These drivers lost control at very high speeds. The result was tragic for one driver and fortunate for the others. But why? What made the difference between walking away and being carried away? The answer can be found in some of the most basic laws of the physical universe. Hi, my name is Griff Jones. I teach high school physics. And behind me is the Insurance Institute for Highway Safety's Vehicle Research Center. It's a fascinating place where research engineers assess the crash performance of vehicles by running tests, and where they evaluate new technologies to prevent injuries, like this state-of-the-art head protection system. What's exciting for me is that this is a laboratory of practical applications in the subject I teach. And because they're set up here to crash cars and analyze those crashes, this research center provides a perfect venue for illustrating the physical laws that govern the outcome of car crashes. So follow me, and for the next few minutes, I'll take you behind the scenes where we can explore the basic science behind vehicle crashes. Let's learn about car crashes and physics. Why'd this dummy get left behind? It's called inertia, the property of matter that causes it to resist any change in its state of motion. Galileo introduced the concept in the late 1500s, and almost 100 years later, Newton used this idea to formulate his first law of motion, the law of inertia. It's why the dummy fell off the back of the truck. It was at rest, and it wanted to remain at rest. That's inertia. It's the same property that keeps the china on the table as you pull the tablecloth out from under it. Now, what about a body in motion? Am I a body in motion? You bet I am. I'm moving 35 miles per hour. But from one perspective, it may not look like I'm moving at all, because in relationship to the passenger compartment, my position isn't changing. But if you look at me from the outside, you can see that I'm moving at the same speed as the vehicle, in this case about 35 miles per hour. And if Newton was right, and we know he was, I'm going to keep on moving at the same speed until an external force acts on me. Now, what does this mean to occupants of a moving vehicle? Watch this. See how the car and the crash test dummy are traveling at the same speed? Now watch what happens when the car crashes into the barrier. The front end of the car is crushing and absorbing energy, which slows down the rest of the car. But the dummy inside keeps on moving at its original speed until it strikes the steering wheel and windshield. This is because the dummy is a body in motion traveling at 35 miles per hour and remains traveling 35 miles per hour in the same direction until acted upon by an outside force. In this case, it's the impact with the steering wheel and windshield that applies the force that overcomes the dummy's inertia. Inertia is one reason that seatbelts are so important. Inertia is one reason that you want to be tied to the vehicle during a crash. If you're wearing your seatbelt, you slow down with the occupant compartment as the vehicle's front end does its job of crumpling and absorbing crash forces.
Newton's second law of motion relates to the motion of an object when an unbalanced force causes a change in velocity. How quickly or slowly the object's velocity changes is called acceleration.
Newton's second law really states or introduces the idea of acceleration. Acceleration of a body will be directly proportional to the force you apply to it, and it will be inversely proportional to the mass of the object being accelerated.
This means that if a large force is applied to a small mass, it results in a larger or more rapid acceleration. If the same force is applied to a larger mass, it results in a smaller or slower acceleration. This is represented by the equation acceleration equals force divided by mass, more commonly stated as F equals m times a.
So it's pretty intuitive that a larger force will create a larger acceleration. A lighter body or lighter mass object will be more easily accelerated than a heavier object.
After learning about Newton's first law of motion regarding inertia, as well as the second law regarding the proportionality of force and acceleration, we are ready to round out the trio and look at Newton's third law of motion. This is most famously stated as follows. For every action, there is an equal and opposite reaction. It means that if two objects interact, the forces they impart on each other will be equal in magnitude and opposite in direction. Think of a car hitting a brick wall. The car imparts an action force on the wall from its motion, and the wall imparts a reaction force right back on the car, bringing it to a quick stop. These vectors are equal in length and point in opposite directions. When hammering a nail into a piece of wood, the hammer imparts force onto the nail, and the nail imparts force onto the hammer.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. We've got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied, according to Newton's third law, by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.